Hello students. In the last section, I was discussing about the motion of the center of mass. So, there I told you when the external force acting on the system of particles is 0, the acceleration of the center of mass is 0, the velocity of the center of mass is constant, and momentum of the center of mass is also constant. So, if the center of mass is at rest initially, it will continue to be at rest. But if the center of mass is in motion initially, it will continue to move in the same path with same velocity. This is momentum conservation principle. So, we are going to see some examples of the motion of center of mass if external force acting on the system is 0. So, let us see. Here I have shown a figure where a shell is going and it is exploding. That is the picture. You have seen this in festivals. The crackers, firecrackers, it will go up and it will explode and it will spread in different directions. Many colors are formed. The same thing I am drawing here. A shell is going like this. It is moving in a parabolic path, and when it reaches a certain point, it just exploded. The explosion is purely due to the internal force which happens due to the chemical reaction which has taken place inside the bomb. Okay, so the force of explosion here is purely internal. There is no external force. And if there is no external force, center of mass will be moving with the same velocity. So, you just see when the bomb explodes, different particles went off in different directions. I have just shown 3 different particles. Different fragments went off in different directions, but the center of mass will continue the same parabolic path. This was the initial parabolic path. The center of mass is continuing the same parabolic path and comes here. So, different fragments will fly off in different directions, whereas the center of mass will continue to move in the same parabolic paths. That is what I have shown here. So, this is motion of the center of mass. Okay. So, this is the first example. You can write and draw the figure. Now, let us think about the second example. A child sits stationary at one end of a long trolley, moving uniformly with a speed v on a smooth horizontal floor. If the child gets up and runs about on the trolley in any manner, what is the speed of the center of mass of the system? That means trolley plus child. Trolley is moving with the same velocity. After some time, what's happening? The child is standing and the child is running in any direction, in any speed inside the trolley. What will happen to the speed of the center of mass of the trolley plus child system? What will happen? The child is now sitting inside the trolley. So, the child is inside the trolley, in the trolley, meaning the child and trolley will act as one system, and when the child moves inside the trolley, it is like the internal force only. There is no external force acts on the body. Okay, there is no external force acts on the body. So, if no external force acts on the body, velocity remains constant. So, in this case, if we take trolley plus child as a system, there is no external force involved. So the force involved in running of child becomes internal, therefore the speed of the center of mass of the system remains constant. So even though the child is moving inside the trolley, the center of mass of the child trolley system will remain constant. Another second example for law of conservation of momentum. Okay, please take down. Now third example. So we have already discussed this in the last video also, but just we are writing it one more time. The linear momentum of the system of particles. So linear momentum means it is the total momentum of a system of particles, and it is equal to the product of total mass of the system and the velocity of its center of mass. So total momentum of the center of mass means it is the product of total mass of the system and the velocity of the center of mass. So I will be writing P is equal to P1 plus P2 plus P3 etc. Pn. What is this P actually? What is this P? This P is nothing but PCM, center of mass. This is also Cm, center of mass. So total mass into velocity of the center of mass. So here I am just writing the subscript as Cm, just to make sure that, make you understand that both of them are the center of mass itself. So PCM is this. So PCM is equal to m into VCM, where this is the momentum of the system of particles and VCM is the velocity of the center of mass. Okay. Now think about another example, the third example, the decay of radium, decay of radium atom into helium atom and radon atom. Okay, radium is decayed into helium and radon. So nuclear decomposition is taking place. So here in the first case, imagine if radium is initially at rest. Radium is initially at rest and it is just decaying into two, helium nucleus and radon nucleus. So what happens? This is the center of mass point I have marked. When it splits into two, helium and radon, helium is small in size, so it moves with a greater velocity. Radon is lesser in size, radon is more in size, so it will go with less velocity. So helium will go with more velocity, radon will go with less velocity, so that the center of mass will be here itself and center of mass is at rest. So before decaying, center of mass was at rest. After decaying also, one will go with a greater speed, other will go with a lesser speed because it is having more mass, but the center of mass remained at rest. Now think about case 2. In case 2, I have shown here radium is moving initially. It was not at rest, radium is moving initially. And at one particular point, that means here, at one particular point, this radium is splitting into helium and radon. As I told you, helium is less mass. Helium is having less mass, so it moves with greater speed. This will have more mass, so it moves with a lesser speed. But since this was already moving, you can see they will move, the fragments will move in different directions. The center of mass will continue to move in the same straight line. Okay, so that is the idea in the second case. So here it was at rest, so it remained at rest. Here the radium nucleus is already moving, so even after decaying, The fragments is going off in different directions, but the center of mass continue to move in the same straight line. Okay. Yes. Now, please take down this notes also. Newton's second law is extended to the system of particles. Newton's second law is F is equal to dp by dt. For the system of n particles, F external is equal to dp cm, momentum of the center of mass. So, here you can write the subscript cm. So, dp cm by dt is equal to F external. So, when the total external force acting on system of particles is 0, total linear momentum is conserved. Also, the velocity of the center of mass remains constant. This is called law of conservation of linear momentum. So, this is the definition of law of conservation of linear momentum. So, please take down this page also. Okay. Now, angular velocity and its relation with linear velocity. We already studied angular velocity and angular acceleration in motion in a plane. When the body moves in a circular path, it will have a velocity, the rotational velocity, that is actually the angular velocity. And when the body is in rotation, there will be an acceleration which is called angular acceleration. So, in rotational motion, we use that word angular. So, every particle of a rotating body moves in a circle. The angular displacement of a given particle about its center in unit time is defined as angular velocity. So, angular displacement divided by time is called angular velocity. So, average angular velocity is written as delta theta by delta t, rate of change of angular displacement divided by change in time. Change in angular displacement by change in time. That means rate of change of angular displacement. Okay, I say once more, angular velocity is the rate of change of angular displacement, or we can say change in angular displacement with time. That is what I have written, delta theta by delta t. Now, instantaneous angular velocity, that is written as omega. Omega is instantaneous. Omega, instantaneous angular velocity, equal to d theta by dt. So, average angular velocity is delta theta by delta t, instantaneous angular velocity is d theta by dt. And there is an equation connecting linear velocity and angular velocity. V equal to omega into r, where v is the linear velocity moving in a circle of radius r and omega is the angular velocity. Okay, v is linear velocity and omega is angular velocity. This is omega, not w. Okay. Now, all parts of a moving body have the same angular velocity in pure rotational motion. That is what you have to keep in mind. If the body is moving in a purely rotational motion, there is only rotational motion, then the angular velocity of all the system of particles remains constant. What is the SI unit of angular velocity? Radians per second. Take down that also. SI unit of angular velocity is radians per second. And I have written angular velocity is a vector quantity. How will you find the direction of angular velocity? So, before telling the direction, you just see this figure. The particle is moving in a circular path. The particle is moving in a circular path here, and one point is P1, and then it travels, that point is P1, then the particle travels, and after some time the particle reaches P2. So the angle how it moves, the angle swept by the radius vector, that is called delta theta, and delta theta by delta t is called angular velocity. So here velocity, the linear velocity v is always along the tangent. That is what I have shown here. The velocity v is always along the tangent of the circular paths. Now look at here. How will you find the direction of the angular velocity? Angular velocity is a vector quantity. So how will you find the direction? It is by using right hand thumb rule. So if you curl your fingers of the right hand in the sense of rotation, then the thumb will give the direction of angular velocity. See, for example, the particle is rotating like this. So I keep my right hand in this direction, right hand is in this direction, then my thumb is pointing towards up. So that thumb is the direction of the velocity. Okay, thumb is the direction of velocity. Similarly, if I hold, see, particle is in a, you just look at my hand, the particle, if it goes in this path, in this circular path, I will hold it like this, then my thumb is pointing towards the board. That is the direction of angular velocity. Now, if the particle is rotating in this direction, then I curve the finger like this, my thumb will go out of the board. So that is how we will find the direction of angular velocity and angular acceleration. So that is what they have shown here. Anti-clockwise, this is anti-clockwise. Anti-clockwise direction is considered as positive. So that is why they have shown here this rotation is anti-clockwise. So it is going in the positive is the direction. That means out of the board. That is what I have shown like this, out of the board. Similarly, this figure, the body is rotating in the clockwise direction. This arc is the clockwise direction. So body is rotating in the clockwise direction, then the angular velocity omega is into the board. That is why the arrow is shown here, into the board. It is not coming like this, okay? It is into the board. I can show with only with that line. Now what is angular acceleration? Angular acceleration is given by the rate of change of angular velocity with respect to time. So I can write alpha is equal to d omega by dt. And what is the SI unit? SI unit of alpha is radians per second square. And this is also, alpha is also a vector quantity. Alpha is also a vector quantity and it is also an axial vector. That means the direction is given by right hand thumb rule. Okay, so that's all in this section. Thank you.